Hello and welcome to the final video, proposition 4.42, except it's not, I lied again, this one is actually the second to last one, and I really hope that I do not end up with another one in between this and the last one. These videos should not be dense around the final one. Anyway, so proposition 4.22, if T is an operator on a Hilbert space H, M is a closed subspace of H, and Pm is the projection onto M, then M is an invariant subspace of T is equivalent to P sub M, Tp sub M is equal to Tp sub M, which is equivalent to the orthogonal complement of M being invariant to the adjoint of T. Furthermore, M is a reducing space for T, is equivalent to that T and P sub M commuting, which is equivalent to M being invariant to both T and the adjoint of T. Now, there's obviously a lot to unpack here, hence the two videos, but we're going to begin by assuming that, assume that M is invariant to T. Now, because of this, for all F and H, we get that T P sub M of F is an element of M. And this obviously because if M is invariant to T, then T is going to map an element inside of M, and everything gets projected to inside of M. So from this we can infer that PM T PM of F is equal to T PM of F. Again, if everything is inside of, if this is going to stay inside of M, then P is going to project it to stay inside of itself. Now, next we are going to get that this implies that TPM is equal to PMTPM because F is arbitrary. So now that we have this from M being invariant to T, we assume this and prove that M is invariant to T. So assume TPM is equal to PMTPM, which gives us, for all F and M, we have that T of F is equal to T PM of F, which is obvious because if F is in M, then this is going to be the identity function. There's going to take F to F, it's the identity on M. And this is equal to PMTPM by assumption, which is equal to PMTF. So T of F is an element of M, which gives us invariance. Note that this does not actually give us commutativity of the two operators because our F is restricted to M. So obviously it's going to commute on M, but we do not have that it commutes in all of H. Now, the next step that we're going to take on is we are going to consider the operator I minus P sub M. Now, the claim is that P sub M orthogonal complement is actually the same thing as this. So to tackle this, we're going to need a little bit more space. So let's revoke what we have so far. And first we're going to show that in fact I minus P sub M is orthogonal to, that the image of it is orthogonal to M. So let's consider F and H. And then we take I minus P sub M of F is equal to F minus P M of F. Then, if G is an element of M, we're going to take the inner product with G and this guy here. What we hope to find is that this inner product is in fact 0. Excuse me, in my notes I actually have the inner product going the other way. That way. Just for consistency so I don't make typos. Now, this is the same thing, obviously, as G of F, G inner product F, minus G inner product P M of F. But now we note that because that there exists this is a closed subspace, M is a closed subspace, we have that there exists an H in the orthogonal complement of M, such that F is equal to H plus P M of F. And what this is saying is that I can always break, if I have a closed subspace, I can always break up any vector in the space into the sum of a vector in the orthogonal complement and the closed space. So we get this equation here, which allows us to then split our guy here. So this is going to be the same thing as, so then we're going to get that G inner product F minus G inner product PM of F is equal to G inner product P M F plus G inner product H, which is minus G inner product P M F. Which obviously these two cancel, which leaves us with G inner product H. However, H was in the orthogonal complement of M, and G is in M, which implies that this is 0. So in fact, every element in the range of our transform here is in fact orthogonal to our set M. Now, next, we need to, so then this would show that the range of I minus P sub M is in fact a subset of the orthogonal complement of M. Now, if G is an element of the orthogonal complement of M, or let's use H for consistency's sake. if H is an element of the orthogonal product of M, then Pm of H is equal to 0, which implies that I minus Pm of H is equal to H, which gives us that this can actually be extended to equality. So range of I minus P sub M is equal to the orthogonal complement of M, because it in fact hits every element in the orthogonal complement of M at least once. Now, the last part that we need to show is that it is in fact idempotent. So I minus P sub M squared of F, so let F be an element of our Hilbert space, we get this is equal to I minus Pm of, and then again we have at the top that this is just Fpm of F, P sub M of F, and this we can then apply the operators, because we can now split our operators. So this is going to be the same thing as F, I applied to F, and then I applied to negative Pm of F. So negative Pm of F. Negative Pm of Pm applied to F is going to be negative Pm of F. And then we apply these together. However, we know that Pm is a projection, so this is actually going to be the same thing as the positive, because the negatives cancel, of P sub M of F. Canceling out these two, we get that this is equal to F minus P sub M of F, which is obviously equal to I minus Pm applied to F, so we get idempotent. We get idempotency. Now, since P sub M is self-adjoining, we have that I minus P sub M star is equal to I star minus P sub M star, which is equal to I minus P sub M, which gives us that P sub M is a projection. And since its range is M is the orthogonal complement of M, we get that it is onto the orthogonal complement of M as desired.